Hi, good morning. Um, so on Friday, the TA will cover for the first 20 minutes. He'll go over the projects and views again, and I should be back by 11. If I'm not here, I'll give him something to cover for the rest of the class. So we will have class on Friday, just not me for the first few minutes, right? Make sense? So do you have any questions about what we covered so far? So one of the things that we are, as we move along with the notion of files and stuff, right? You will begin to notice that they begin to look sort of like the memory system, with there's some similarities, there's some differences, and as you move along, you tend to notice that they kind of begin to merge a little bit, and some of the concepts are what we'll see in today's lecture, right? Starting with this notion of a temporary file system, RAM file system, which is what sort of I left off at the last lecture. The idea here is, one of the things that people noticed is there are a lot of temporary files which are created, which look like files because they're you create them in a file system, you give them a name, but you don't really expect them to stay around for long. Meaning they get created, somebody writes into them, and somebody opens them, reads them, and then deletes them, right? For example, one of the things that happens is if you try to, say, compile a program, C program, right? If you do the GCC -V, you will notice that it goes through multiple different steps, right? For example, it might do a compilation, 2 steps of compilation, and each of the steps may create different files. So essentially, you take your .c file, you make it a .i file, which some other program reads it, right? So this program will open, write this file, close this file. This program will open, read this file, close this file, and then delete this file, right? So it's going to create another output, and which is going to get another output, and so on and so forth. So there's a last output, which is probably your executable file. So what you really want is the .c file to stay and .out file to stay. All the intermediate files, if the system were to crash, and if these files tend to, the files were lost, you probably won't notice it because you didn't create them. They were created by something within the compilation process. Right? So for these things, what they're really trying to do is create a shared memory. Right? They're creating a shared memory such that this process can send something to here. They're using the file system to send something, but they're not really creating a file. Right? They're not creating a file which has to exist forever and all those things. So one way to speed up the system would be to treat them as memory, right? Read them like a shared memory. And the way to do that is to take your virtual memory and build a file system on top of it, right? You take a big chunk of memory and build a file system on top of it, and you can very easily do that with your fuse, right? So it'll look like a file system, it'll act like a file system. Everything you write into it will act like a file system, except when you reboot the system, everything is gone, right? And if it's gone, so if you boot back again, your .c file will stay, your .out file will stay, any of this stuff could be gone, right? And that improves the system performance a lot. And that's one of the optimizations that you tend to do. And the thing you notice is, if you make this into virtual memory, remember the virtual memory system from last module, right? So if you're running out of pages, you will begin to swap them into swap disk, right? So now you have this funny notion that you want to avoid writes. So you create this chunk of memory into a file system, but the file system itself may be swapped out to a swap disk, so it may actually go into a disk and come back, right? So it's sort of like a file system, sort of like a virtual memory. It's sort of this kind of a weird notion, right? Does that make sense? You allocate some chunk of memory for your file system, which you don't really want to go to disk. But since it's a virtual memory, all the things we learned from last class comes in, right? If you run out of virtual memory, then you will have to replace some pages. So you will choose one of these pages just like anything else, and those may go to swap disk, those may come back from swap disk. As long as things are kind of okay, you don't notice much of this problem, so you're kind of okay, right? But that may happen. So actually, even though you didn't want them to go to disk, it may go to swap disk, and the same kind of penalties and stuff. So you're kind of blurring the notion of what is files and what is memory. You're treating them like a memory through this file system, but it does get to disk because of the swap notion, right? Does that sort of make sense? Right? So you begin to notice this kind of behavior, right? And this is the notion of temp file system. To give you a sense of how these things work, I logged into one of the CS, the machine Wizard, which is a Solaris machine. It's true for all Linuxes and Mac and all those things. So there are a couple of commands that you can use to figure out what is the file systems in a currently executing system, right? One is a command called df, which shows all the display file systems. And I think it's kind of going off the screen. But essentially it tells you that this is the file system, right? The first entry is a file system. And this is the size and how much size is left and where it's mounted, right? Let me try to make this a little smaller. Can you see the size from the last row?
Yeah.
So if you look at the output, the first is the file system, and the next one is the size of the file system, how much is used and how much is available, and how much of the capacity is used, and where it's mounted on, right? So this particular file system, let's say this particular file system is mounted on here. That means if you go to /user/vice/cache, you're really accessing that file system, right? And you can look through the stuff to see some of the stuff you may recognize, right? So like for example, /temp and /var_temp is really in swap, right? So that means they are really a temporary file system. So if you write into /temp on this machine, you're really writing into swap, which is really the virtual memory based memory file system. So anything you write here, when the machine reboots, is gone, right? Which also means that these things will be very fast. So one of the other commands that you can use to copy files in and out or create files on a quickly is this program. Let me write the command. So this is this command called dd, which is like a disk dump, which is essentially like a low level, it creates like a backup kind of thing. So this particular program takes input file, it reads from this file, it writes into this file, and the block size that I want to write, it writes in blocks. So I'm just going to give 4096 a 4K block just for trying it out, and count. So I want to create 4000 blocks. I want to copy 4K blocks, 10,000 of those, right? And I'm going to read from this file called dev0, right? This is a kind of magical file in Unix. If you read this file dev0, it'll keep giving you zeros, right? So if you read 1,000 times, you get 1,000 zeros and so on and so forth. So this is a quick way to create any size file that you want. All the entries in this file will be 0. So essentially what I'm trying to do is, I'm trying to create a file called /temp/file, right? With 4096 blocks of 10,000. So it's essentially 4096 times 10,000. That big a file I'm going to create on the temporary swap file system. I'm going to time it to see how fast it takes, right? This is a way to see how quickly we can do this stuff. Oops. So I created 10,000 records in about 0.33 second. You can see up there, right? So the user time is 0.03 second, and the system time is 0.29. So the overall time is 0.33 second, right? To give you a sense of how bad it would be if I do this in my AFS space, which is a distributed file system, right? I do the same thing. I'm trying to create a 4096 times 10,000 block, and it's still creating. So it took about 15 seconds, right? So if I actually were to use this on the real disk, I mean, again, there are caches and stuff, but even then you can notice that if I use the memory file system, it's so much faster, right? You go from practically 1/3 of a second to about 15 or so seconds, right? So having this temporary file system is a really good thing, because all these temporary files get created really fast. You completely ignore the notion of persistence, but that's okay. Your compilation and all will go much faster because of this stuff, right? So you can use these commands to kind of test your file system to see how fast things are on a rough estimate, because of course with caching and stuff, if I want to do something over and over again, then things get cached and all those things, but at least the first run should not be cached. You should be able to get a good sense. Make sense? That gives you a sense of how why you would want to do a memory file system, because those things are way much faster than what you can get from a disk-based file system, right? So the next notion is something that we didn't cover from before on chapter 9. We'll look at that here, right? That's the notion of a memory map file, right? So far we have looked at two concepts, right? There's a notion of if you in your program you have a chunk of memory, right? Going back to memory module, you have a chunk of memory, right? And you write into it and you read from it and so on and so forth. Virtual memory basically means that if this gets full, it writes into a swap disk, right? It creates a swap disk. It has notion of blocks, same like what you see in the file system, because it's the same disk you may write into. So you have these blocks. So what happens is virtual memory basically keeps anything you write here, it stays here till it has to be replaced. At that instant, it has to be returned here. Other it may be brought here, right? So the virtual memory system basically moves pages back and forth between here to make sure that it manages the memory for you, right? So that's what virtual memory system does, right? And if you think of them as files, right? You want to create this notion of a file, which means that it has to go into the same kind of disk, the same kind of blocks, and so on, right? When you use the file, you have the notion of open, close, read, and write and everything, right? If I exactly follow the right model that you call from your program, the performance of this thing will be really awful, right? So for example, if you have a loop which says while 1, write 1 byte, right? You go through a loop and you're writing 1 byte, right? This would really mean if I have to do it exactly what you meant, I would have to read the block, because I can't write into the block, right? So I have to read the block, write the block, right? So every iteration, I would have to read the previous block, modify this one value, write it back, read, write kind of thing, right? Your performance will be really, really awful. So no operating system would want to do that. What it will do is, you'll try to have a buffer here, and every write you send to it, you'll keep collecting it, and at some point you'll write it back to the disk, right? So if you look at this model, right, so logically you want to do this, but essentially what happens is everything gets collected here. At some point it's going to decide to write it back, right? They look awfully similar, right? The same notion that you keep writing into this buffer, and at some point somebody decides to write it, right? The only difference here is when this program exits, you don't have to flush the contents from here to the disk, right? Because if it's a virtual memory, if your program exits, you don't care about the memory, so you can flush it. So if you remember from your last homework project, you don't have to count the last dirty pages because your program is exiting, who cares? Whereas in a file, when you exit your program, when you close the thing, everything here from this buffer has to be flushed, right? Other than that, your virtual memory is already doing all this stuff. It is maintaining all this notion of a small amount of memory, right? We may call this logical address space, and here we may call it buffer, but the concept is the same. I'm writing something into here, and the operating system decides when to write it, right? The only difference again is you know this is a file, so you want to make sure that this write is happening more often than it's here, but otherwise it looks sort of the same, right? So the idea next is to kind of merge these two, right? Why build the notion of a files? Why build the notion of a virtual memory? System is going to have virtual memory anyway, so why don't we kind of map the notion of files into virtual memory, right? And that's the notion of memory map file, and that's used a lot. So the idea here is you make think that you're opening a file, but what I really do is I kind of take this file. So if your file happens to be here, right? I map this area into a segment, just like you would do there, right? And map it here. And then I give you the pointer to the start of this stuff. You can treat this as a memory, just like you would do on the virtual memory system. But I promise that everything you write here would be written back at some point, right? So you will kind of blur the notion. So that's the notion of memory map file, right? And we'll see an example of how this is done. So the idea is, since both of them look awfully similar, there's only slight differences. You could reuse the same concept within the file system, within the operating system. You don't have to repeat the code, and you may actually get better performance because if you really tune the virtual memory to be very good, right, it may decide to write these things at much better scale than what you can do in your program. Like I said, if your program was to do exactly what you wanted, it has to read this buffer and write the buffer all the time. Rather than make one set of decisions for files, one set of decisions for memory, you may try to merge both into this notion of memory mapped files, right? And so the idea here is, once you did this, now your file becomes part of the virtual memory, and you can do the sharing just like you would do for virtual memory, and so on and so forth, right? Once you do that, actually, you could create. The nice thing with this model is, many of you, when you write files, right, you read stuff from the file. You create internal data structures like with pointers and stuff like that within your program, and then when you want to write it back, you serialize it. You kind of read the whole thing and write it back, right? So for example, if you want to create a tree structure, you would read all the records from the file, build this internal memory structure called a tree. But when you want to write it back to the disk, you would walk the tree and then write only the leaf nodes, right? Does it make sense, right? You don't actually write a whole tree data structure into the disk because you want to get the stuff. But whereas when you do this memory mapping, you could leave the complicated structure as it is, right? As I'll show that with an example. So here's an example using memory map of a file system for a file. So again, here we're taking the notion of a file. This is a POSIX code, right? So what I do is, this is a simple program which you realize from earlier times, right? I open a file called path, which happens to be file, right? I open it for write only, create, and trunc, which means that if the file exists, I delete it. I basically create a 0-byte file, and then I write hello world, right? Hello space world. I could have put it into one thing, but for some reason I did twice, and then I close it, right? So this way, you expect at the end of this run, your file called file will have hello space world, right? So that's written into this file, right? This is the traditional way you think of how you do this with the files, right? So to do with mmap, right? Ignore all the bits. You can look at the manual pages to see what those are. Essentially, what I'm trying to do is I want to map this particular file into my address space, right? And the mapping happens such that pointer will now point to the file from where I mapped, right? So I'm going to map this particular file with these flags, right? I have to first open the file. So ignore the arguments. You can look at the man page to see where the arguments are. But essentially, I map this file into my memory, which means that now this variable called ptr would point to this file as a memory, right? So I can do all the things I would do with memory. I can do a ptr plus 2, which is basically I'm sort of seeking to 2 bytes, right? And actually, I said I started from. So I copied this stuff, right? I copied LP. So I basically copied LP starting from address. Okay, so I copied 3 bytes here. Can you see what this will do? The mmap, what I did was I mapped the first 4 bytes starting at 0 bytes. And I did pointer plus. So when I did the mapping, pointer was pointing here. Then I did pointer plus 2, so it goes here. right? Right? And then I copied over LP space, right? What would happen to this thing? It'll become help space world, right? And then I do a mmap. That's part of the unmapping, which is sort of like the close. Then you close the stuff, right? So this piece of code would modify hello world to help space world by treating this contents of the file as a memory program, right? Do you see how it's done? So people who use memory map will find it very, very useful. They can do like really weird stuff within with mmap and stuff, right? A lot of your libraries use mmap and stuff because essentially you're treating them like a virtual memory. So all the things you did for virtual memory hold. So even if you unmap it, it may still be left in the virtual memory because that's part of the memory system optimization. So for example, you can write a code like this. Suppose you want to have a data structure which has two entries, which has a value and a pointer, right? And I want to have this value is 2 and then this pointing to another structure. This is like a very simple linked list structure that you may want to do, right? Essentially, it has two linked list structures. This pointer points to this entry, right? And you have this linked list structure. In a traditional file, you would probably write it as you would write 2 in some sort of a separator and then say 3, right? Then you have to build this linked list again, right? Whereas if you do a mmap, then essentially you had PTR, right? So I can treat this as a memory, this as a memory. As long as it is relative to this pointer, I can write it as it is. I can write with the pointers, right? So I may be able to write into the disk 2, and let's say this was 0, and this I happen to assign it as 100. I can write 200, 3, 0, and when I read it again, I could reconstruct these pointers because they're still part of my map entries. Does that make sense? So you can actually write this whole data structure into file and then bring it back. As long as it's relative to where you started from within your mapping, you can do something like this, right? So this may be a very powerful way for you to do this stuff. And if you do any kind of serious program, you notice a lot of times you're just writing back and forth into the disk. You're trying to change this abstraction of memory with pointers and all those things. But when you try to write to disk, you're trying to do this write, read, and seek and all those things, which are another kind of abstraction. With this model, once you figure out how to do this mmap and mmap, that's all you have to do. And after that, you can treat this like memory. The only thing you have to remember is this is mapped to a file, so anything you modify will eventually go back to disk. So anything you modified here will modify the disk, and so on and so forth. And most programs, most real programs will use mmap, right? So yeah, that's the. Is that clear? How to use mmap? Again, this is part of the trend that suddenly you notice that these two are sort of similar, sort of different. The the only difference in files is you have the same concept of memory, but you want them to survive through. You want it to be persistent. Here you don't have to be persistent. So now you kind of have to merge both these things to get better performance. And then you have the notion of caching, right? I've kind of mentioned that writing into the disk is very slow. So you want to do some sort of a caching, right? So you end up having two kinds of cache, right? One is a page cache and one other is called a buffer cache. I may call it differently, but essentially what it does is page cache is a cache for your paging system, your memory system, right? And buffer cache is a cache for your file system. But essentially they're doing the same thing. I'll just give it a different name. But essentially what I'm doing is page cache is a cache between your memory and the swap disk. Buffer cache is a cache between your program buffer, your program writes and the disk, right? So we have these two different concepts. If I built them separately, if I didn't think about them as two different concepts, I would have a page cache into your operating system. I would have a buffer cache into your operating system. They sort of doing the same thing for the most part, but not quite. I mean, they have a little bit difference, right? Page cache, you have to remember when it's not needed, you can just throw it, right? If you exit the program, you can throw the page cache. Whereas if it's a file cache, it has to be pushed back to the disk. You have to be a little bit more aggressive on the buffer cache because, I mean, again, when if the machine was to crash halfway through, you don't want the stuff to be in buffer, right? So if you have a buffer cache and you keep writing into a file, and you keep writing into the file forever and ever and ever, you don't want to kind of wait till the end because eventually you have to be a little bit more aggressive on writing to disk. But other than that, you have the same thing, right? So I may call them as page cache and buffer cache, but they sort of the same, right? So earlier operating systems didn't think about them as two different concepts. So they had the notion of page cache and buffer cache and file system. This is how they sort of built it, where page cache, since it's a memory cache, it builds off of the file system cache because it's writing to a swap disk, which is a file system. So you end up having this different hierarchy, right? Which essentially would not be much of a problem for you as long as you only went one way, right? If you do a memory map file, you went that way. If you went this way, you went this way. Life was good, right? But once you have this memory map files and you try to do both, you try to treat the same file as a file or as a memory map file, you may end up going through these two ways, right? Which means that you may access the same file as a file and as a memory map file on the same program or different programs. The one which treats it as a memory map file would go through this model, which means that it will first have a notion of a page cache, and when the page is replaced, it gets pushed to the buffer cache. If you're treating it as a file, you don't have explicit buffer, so it goes to the buffer cache, right? Does that make sense? So what will happen is sometimes this IO may read something which was already modified here, but it's on the page cache, right? So if you wrote two programs, one of it treating it as a file, one of it treating it as a memory map file, since you have these two buffers, it may happen that this read will get some contents which has already been written or modified by that program, but it's being in that cache, right? So you end up with this problem of you cannot mix both, because if you mix both, then some entries may be inconsistent, right? So that's the problem you run into. So the solution is to unify both, meaning like get rid of both the caches and essentially come up with this, right? Which is memory map IO and the whole system now has only one cache, right? So the whole system, module 3 and 4, essentially will have only one cache. That cache will be treated as page cache or buffer cache, depending on how you go about it, right? And it kind of started off with being memory map IO kind of stuff, but in the general scheme, this is a good thing, right? So essentially now we have only one page replacement policy that you had from the last module, right? You may, as a programmer, treat it as a file. You may call seeks and what have you. You may call it as memory mapped or whatever, whichever is easy for you. But essentially, all of them are trying to do the same thing. So now I kind of merged the virtual memory and the file system into the same thing, right? I may, as operating system, kind of keep track of notion that these are part of buffers and these are part of the page. So I may flush them to disk at different rates at different whatever. But the entire system is now one thing, right? There's this notion that you have something that you operate on, there is a cache, and that flushes back to the disk, right? So the backing store may be a swap disk for memory system. It may be a file for your program, right? But the concept becomes unified in this unified buffer cache. Did that make sense, how these two modules are really the same, even though they are different? Right? You may have little policy tweaks. I mean, if you want to optimize for stuff, you may want to avoid some things. So for example, if you have page cache, you may not want to write it that often because you're a page cache kind of thing. But there is really not much of a difference, right? Essentially what you're trying to do is you're trying to capture as much of stuff as possible closer to the application, right? Remember the hierarchy, right? I want to keep it as much closer to you, as much in the cache rather than the disk. And you want the flexibility for the operating system to flush it into the disk when it wants to. You don't want it to do it every time that you write because then your performance will be really, really, really awful. So you want these things to do something smart, right? Rather than creating two smart systems into the same operating system, you want to have one smart system and kind of tweak it a little bit for whatever you want to do. But essentially have one scheme which you may access it in two different stuff, right? Can you think of a reason why you would want to keep one way of doing stuff rather than two ways of doing stuff within an operating system? Yes?
Maintenance of redundant pieces of code.
Yeah, same reason that you will have for your homework projects and stuff like that, right? The more code you have, the more logic you have, the more possibilities for bugs, right? Operating systems are no different. I mean, operating systems may have lots of people operating on the stuff. They're trying to make sure there's no bugs, but you still run into bugs and everything, right? The lesser amount of code you have, the lesser complexity you have, hopefully you will be able to debug them. You'll be able to have some sort of a sanity because you have only one way of doing things, right? You want to avoid having two different things sort of doing the same thing but a little bit different. So if you try to modify one, then the other things will break kind of stuff. So you want to keep them into as one policy, one kind of system. So it reduces the operating system complexity a lot, right? Because otherwise, remember in the last case, you have this page cache and the buffer cache, and the other way going through directly to the buffer cache. That means you'll have to make sure that there's some code which says if the file is already open in mmap, then look into the page cache first, then before going to the buffer cache. Then you add all these complexities. You're maintaining a page cache separately, you're maintaining a buffer cache separately. And you're also now trying to make sure that if something gets accessed halfway through, then you want to make sure that you look in the page cache. If not, look in the buffer cache. Things get messy. But with this one, you kind of make everything simpler, right? So most of your programs, most of your PowerPoint and all those serious programs use memory map files. They don't actually do this open read and write and everything, right? Those are simple enough for you to use, but once you begin to write more serious programs, memory map files are really, really nice, right? And I didn't actually go through the notion of what those bits are, right? So if you remember there's this notion of protect, read, write, and share and stuff like that, right? We'll see a little bit of that in the last module, notion of protection. But actually, you can actually do a lot of nice stuff, right? So here you're saying, I want these things to be mapped, but I want this protection to be read and write, right? This is the concept you had from the memory module, right? Memory module, you had the notion of segments which are read only, write only, or execute only, and all those things. You can give those things to this program, right? So what this could do is essentially you're saying, I want to map. Actually, the code here is I want to map starting at 0 for 4 bytes, right? I want to map that segment as read write into this pointer, right? So what would happen if you try to modify this bit? You'd use that code. I'm saying says map. So actually, there's a bug because I've tried to modify till here, right? Let's say I mapped till here to here, right, into my program, and then in my program I tried to modify this D, right? What do you think would happen? What do you think should happen, or what do you think may happen? This goes back to the memory concepts, right? You may get a segmentation fault, right? Because if you do the right way, you're trying to say, I only want to map these 5 bytes, right? I'm saying there's a bug here because I modified till here. So this should have been 5, right? Right? So you're saying I only want to modify certain bits here, right? This mmap did not map this into your program in read or write or whatever, right? So if you try to read this, your operating system may give you a fault, right? Depending on how it's implemented, it may be within a block and all those things, but in general, you may get a fault if you try to read this. You may get a fault if you try to write this, right? So your program can actually be more complicated. You can actually use this read and write notion to compartmentalize and say, you as a function are only allowed to modify this part of the file. You can't really touch any of this stuff because if you do, you get a segmentation fault, which is a concept you got from the memory system, right? Otherwise, as a file, if I give a file descriptor, you're free to modify any of those stuff, right? So I give you more power that you get from the memory system. So when you write these programs, you can actually selectively only map little pieces and chunks right there. So you're sort of getting for free this notion of even if your program was to have a bug, it cannot possibly write more than what you map because anything else would give you a fault. And that's a concept which comes from memory. So as a programmer, this is a really good thing because now it's file descriptor. I can modify anything with the memory notion. If you try to modify something other than what was mapped to you, you get errors. And you can play with those bits. So you can actually write really powerful programs by playing with those bits, right? How to use them is beyond the scope of what we're going to do in this class. But if you have time and if something that you would like to look at in terms of files, look at the mmap. Mmap can do really, really nice stuff at the user level. And you'll see most of the programs tend to use mmap. Right? So essentially at this point, they're both the same, even though there's like little differences, but they're kind of underlying. Under the hood, they are the same, right? The two modules, except one has to go on the disk and stay in the disk. From your perspective, they're different, but from the OS perspective, they may or may not be the same, right? So this is one of the reasons why when you buy more memory, your system, it's kind of hard to tell how much free memory you have. If you you can look through different stuff, but it's never clear to you exactly how much memory you have because of all this stuff. There are different kinds of caches, some used for memory, some used for file systems. They're all taking memory from the same general pool. The more memory you have, the better performance you get. But it's kind of hard to pin down which is actually being used by you, which is actually sort of there, right? Everything that you operate is mapped into your virtual memory, and the swap, it moves back and forth between the swap. And the question of how much free memory you have in a system is kind of ridiculous. So when you see those applications which say, if you run this with your PowerPoint, it'll clean up your memory and it'll give you a lot more free memory, it's meaningless because you want to do all this kind of stuff. You want to keep moving stuff. You want to have as much cache as possible. You don't want to be nailed down and say, this is free memory, not being used by anybody. That's a waste. You don't want things to be free. You want it to be used by some buffer, right? So there are other things when you have with the files when we kind of looked at them as we moved along. One is the notion of if you ever mess up something on the disk, right? If you get messed up with your directory entries or what have you, you have to have some program to clean it up, right? Because the file systems, if you mess something up, you have to do some operations to clean this up because otherwise you'll have blocks which are allocated but not being used anywhere, right? Or files which are pointing to the same entry and all those things. And the programs is either scan disk or FSCK in Unix and so on and so forth. And essentially, they're trying to go through the file system to make sure that all the links are fine. And depending on how complex you want it, it may take a while because it has to go through all the files and figure out which is free and stuff, right? So they're done in two different modes. In one mode, they try to make sure that you're good to go. In another mode, they go and clean up all the stuff. They may pick up entries which were not allocated to anybody, but nobody knows about it kind of thing. So if your free block entry is wrong, you go through a more elaborate process to figure out all the files accessible, right? And another way where you just make things go, the wasted blocks are left wasted, but you make progress, right? And one of the ways to solve this problem, people notice that regardless of how you try to do the stuff, things always get messed up because there's so many caches along the way, right? There's one cache we're not talking about here, which is underlying all the stuff, which is the disk cache, right? When you buy any of these disks, right, the disks are not, the storage that you're buying is not a dumb thing. We'll see about how disks are organized in the next chapter, but they're not a dumb thing. They actually have some cache, right? So most modern disks have 8 to 16 megs of cache, which means that if you go from the buffer cache and you push it to the disk, it's not really actually going to the disk. It's actually going to the disk cache. And disk is running a little operating system inside, which decides when things should go actually to the disk, right? Which means that you really have no control over when things are actually written on the disk. So even if I say this should be written on disk, I can't be sure because there is another operating system inside the disk which is making decisions. So you'll end up in cases where even though you think you're writing something, even though you are pushing it from the buffer cache all the way to the disk, nothing goes to the disk and you run into problems, right? And the only way to deal with that is to run the scan disk, and it can take forever and ever. And as you begin to look at larger and larger file systems, if you have a several terabytes of file system, then it'll take you days to do the scan disk, right? So one way to avoid this is the notion of a log structure file system. What it does is it essentially does something that we were looking at before transactions and stuff, right? What it does is every operation you do, it'll log it, right? So now it creates 2 copies, and so it creates a buffer. This is essentially what it does. So suppose you have, let's say you're operating on 4 files. There are a couple of programs in the system which are operating on 4 files, right? And you modify this little something here, this little something here, this little something here, this little something here, right? So since they are all in blocks and stuff, you want to keep them in cache. You don't want to write them until you need it to, kind of thing. So this is still dirty, hasn't been pushed to disk, 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 right? And then you want to do the right thing and push them to the disk whenever you want them and everything, right? You get better performance by keeping them in memory, right? But you also want to write them to disk, right? But you haven't written enough stuff to push it to disk. You can't really change the system to say these things will have to be pushed to disk all the time. Then you lose performance, right? The way you solve them is to have a data structure called log, right? I write it like this, but essentially it's just a block, right? Every time you modify this, I log this entry, basically saying on file 1, right, this offset to this offset to this offset, I wrote this new value, right? I log what I did into this stuff. I log what I did into this. I log what I did into this. I log what I did into this, right? And if I were to overwrite it, I log what I did into this, right? Even though those 2 updates cancel each other, right? If I keep modifying a variable, the updates will cancel each other. But I'm going to log it into this thing, right? Can you see what that does? Since I'm creating these logs at a much faster rate than what I'm doing here, this is going to get filled up much faster, right? But those blocks are going to get much faster. So I can keep writing them to disk, right? Because those things are write once, and you don't have to modify. You don't have to do anything to them. You're just writing them to the disk. So essentially, you are creating a log entries into a block. So these blocks you're writing much faster because these are being created at a much faster rate. So they capture all the modifications you're doing to the disk. You don't have to capture reads, but you're capturing all the writes to the disk, right? So now you have all these things written to disk, right? So now you have this log entry. So eventually, when at some point, if this was written to disk, right, and you know it's written to disk, you don't need this stuff, then you can go in the log and say, there are 2 log entries here, which were capturing what was happening here. Those have been written to disk, so you don't have to worry about these entries, right? So you can go back into the log and clean out all the stuff that are no longer needed because they have already been reflected on the disk, right? And then you're kind of left with some entries which have been modified, which are still logged, but is not in the file system, right? So if the system was to crash at this point, all you have to do is log replay. So when you boot up the system, the first thing it has to do is go through the logs and say this entry here which is still valid, which means that this has not been reflected. So you just take this entry, update this particular block. Take this entry, update this particular block, right? And then you come to this entry and you say, okay, there was a log entry here, already been reflected, so I don't have to replay this log entry, right? So I go through this log like this and make sure that after I do this, whatever operations you did now go into the file system, right? Does that make sense? That's the notion of log structure file system, right? Essentially, you create this log of everything that you're doing, right? You're getting 2 copies, and since these are logs, and since these are being returned in a sequential fashion, they tend to get flushed more often, right? You can also make them flushed more often because you know they're logs. And as long as these logs are better written to disk, when you boot up the machine, all it has to do is first replay the logs. So if any of you run Linux or Mac or something, or Windows or something, if you look at the logs, you'll say replaying logs, right? It'll say replaying logs from 10,000 to million or something. And it'll go through them really fast because you can read to them really fast and then make the modifications, and then you're good to go, right? So the next challenge is what to log here, right? In the example I was talking about files, modifying the files and everything, right? You can either have logs for directory entries or logs for files, right? How do you expect the logs to grow if you're operating on directories, and how do you expect the logs to grow if you're operating on files? If you're operating on directory entries, right, where you're keeping track of files and all those things, how fast do you expect them to grow as compared to if you're capturing every modification to every file? Which one do you expect to grow like really fast?
File modification would go really fast. Directories not so much.
Yeah, the file one would go really fast, especially if you're just writing whatever you want, right? If you're just modifying this little bit of piece of stuff, it's one thing. But if you're doing what people normally do, which is read the whole file, write the whole file kind of thing, then your log would be as big as the files. So your log size would be growing so big that you probably need half of your file system for the log or more, right? Because like I said, every modification has to be returned, right? Even if it cancels each other, you'll have to make these stuff. So what typical file systems do is, even for log structure file systems, they only log metadata, not the actual data, right? Metadata in this concept is essentially the directories. So you only log the directories, not the file. So when you reboot the system, you replay the logs really fast because you're too lazy or you don't want to pay the cost of logging the whole files, right? So when people talk about log structure file systems, most of the machines you use are log structure, right? So if you really want to see how it is, go back to like Windows 95 or something, pull the plug halfway through, run the scan disk from the beginning, right? You'll see that it'll take hours and hours. But now if you reboot the machine after whatever, if you just pull the plug, reboot the machine, things seem to go much faster because you're doing these log structure stuff. And the only thing that is capturing right now is the directory entries, which means that your file modification may still be lost, but at least you'll be able to see this is a file, right? Which may or may not be what you thought you were doing, which is may or may not be what you're getting, but that's what you're getting, right? Because the other way is too slow or too hard, so we don't try to do that. So essentially what you do in most of these log structure file systems is you log the directory entries just because it's easy to do. You don't log the files because it's very hard to do, right? And unless you're on a server or something, you don't really worry about these things, right? So that's one optimization which makes your life a lot easier, and that's one of the reasons why you can have gigabytes of files on your laptop and stuff. So even if you lose the power, the scan disk seems to be much faster, and you're able to make progress because it replaces the stuff, right? But you have to remember that it still is not solving the problem of file corruption because that's a separate issue. So it may be the case that something that you modified was lost because it was never written to the file. So you may have to once in a while run the whole real scan disk, run the real FSAK to clean those up. And if any of you run those, it takes a long time, right? Like Linux and all would do that every so often, it'll run the whole thing. It's a very slow process, and you have to do that because of the notion, right? The other way that server file systems deal with this problem is through a notion of a non-volatile RAM, right? So most of the big servers that you buy, if you buy like a server that like Notre Dame has, they have a big chunk of memory called non-volatile RAM. It's battery backed. So essentially all this cache goes, so all the logs go into the NVRAM. So even if you lose the power, you store everything on the NVRAM, so you get some more, you get some benefit. And those things tend to be expensive, right? So you don't want to do this stuff all the time, but not anymore. The future is towards better flash memory. Right? Flash memory is getting cheaper and cheaper. In the future, your laptops will have some, I think it's already happening, right? They call it hybrid disk or whatever. But essentially, you'll have some chunk of memory within your laptop, which is stable, right? So you want to write these logs as fast as possible. So the larger memory you have, like if you let's say if I have gave you 50 gigs of flash memory, right? So then I can think about writing all the logs into that flash memory as fast as possible. So I'll be able to do not just the directory but also the flash. But for that, technology has to catch up, and we're still waiting for those. And in that case, you will not have file system corruption and stuff. And we'll continue with the mass storage, how the hardware really works on all this in the next lecture. And one of the things to remember on all this stuff is, if you really understood how file systems work, you should be scared, because you're probabilistically getting what you stored stay in the system, right? When you write something, we never make a guarantee 100%. We don't even make 99%, right? The guarantee we are making is very, very poor, right? And we kind of live with that, oblivious to what is really happening. And the problem is not solved when you do a backup, because backup is still backing up that corrupted stuff, right? It's beyond the scope of what we're trying to do. But if you want to know something more about it, I can give you pointers on how bad things are with the file system. Because you want to get performance, and sometimes things fall through the crack, right? I'll see you guys a little bit later on Friday.